All right, let's talk about this first FRQ. It's on rotation. In an experiment, when students release a disk of mass radius of r from let's say the top of a ram that makes an angle theta with the horizontal. Disk rolls without slipping. Um, that's a very important information. As shown in Figure 1, the rotational ratio of the disk is half mr square, and the friction force exerted on the disk is Ff. On the diagram, figure 2, draw and label arrows that represent the forces, not components, that are exerted on the disk as it rolls down the ramp, which is indicated by the dashed line. Each force in the diagram must be represented by a distinct arrow at which the force is exerted on the disk. So we know that as soon as it is released, its velocity is going to increase, right? Because of what? Because of mg sine theta. This mg sine theta is going to act here. And since this is not slipping, it must roll or rotate in this direction, right? Because that is the condition of pure rolling, right? That V and omega r are equal. So that at the bottom, the V is forward of the center of mass and omega r will be pointing backwards in this case if it is rotating in this fashion. I'm telling you this information because it's helpful to denote the direction of the friction in this case. So in inclined plane, whenever an object is released, friction has to act in this direction. So friction is going to act, this is the point of contact, and it will act backward over here. Then we have a normal reaction. A normal also acts at the point of contact, so over here, something like this. And mg is going to act at the center of mass, which is over here. And this is going to look downwards, as I can denote it as fg, or probably I can say mg as well. Both are okay. The mass is capital M, sorry, capital M times g. So that's how we represent the FPD. The next one talks about starting with Newton's second law in the rotational form. In the rotational form, there an expression for the net torque exerted on the disk in terms of all these quantities. Begin your derivation by writing a fundamental physics principle on an equation from the reference book. Now, it's very important to understand that since it is rotating to the right side, I think I already mentioned that is the reason why friction is acting backward, because it is the force that is the only force that can provide the torque, right? Because this cannot provide torque, normal reaction, because it is 90-degree to the motion, or rather it is just acting. uh, the displacement is over here and this is 90, so it cannot really offer any torque. Mg cannot really offer any torque for the same reason, because it is acting at the center of mass. So once again, R is 0. So only friction is able to provide the torque, and hence the rotational tendency will be like this. You don't have to show this on FBD, but yeah, it is like this. Okay. Now, since they're talking about Newton's second law in rotational form, I'm going to say, what is the Newton's second law in rotational form, by the way? Just like the translational form is F is equal to ma, so rotational form is torque equal to I alpha, right? Determine an equation for the net torque exerted. And like I said, the only torque exerted is actually the friction. Okay. Now, since this torque is only because of friction, and friction is Rf sine theta, right? So I'm going to write r, which is the radius, that is capital R, is small, the friction Ff times sine of theta. And remember that between the friction and the displacement, between the radius and the friction, the angle is 90, and this is equal to I alpha. So this becomes, I think, R times Ff, because sine 90 is anyway 1, and that's equal to half mr square times alpha. So R and R is gone. So I have 2 times FF by multiplying 2 both the sides and dividing by MR both the sides. That's the alpha. And this alpha I'm going to sub in over here to find the torque, because that's what they need after all, net torque. So the net torque is going to be tau net is I alpha, where I is half mr square and alpha is 2 times force of friction over mr. So this 2 and 2 is gone, m and m is gone, and r is gone. So I have F of friction times R. That will be the net torque over here, which is pretty much the same thing. I already got RF as the net torque over here, but for some reason they wanted me to start with this Newton's law in rotational form and eventually find alpha and then plug that back in to find the torque. Anyway, so that will be the net torque in terms of FF and R. There are no theta and M involved over here. Then they are asking us to start with Newton's second law and derive an expression for the net force exerted. So the net force exerted will, of course, be, we need to make components over here, right? So I'm going to do that. Let me make the components over here. So this is the disk. We know that this is going to be mg sine theta, providing the acceleration. This will be countered by the normal reaction. Normal reaction is, of course, acting from here. Normal reaction. This is mg cosine of theta, and then we have a friction force that is acting backward. So these two are the required forces, right? And let me denote friction with FF. These are the forces that are responsible for the linear acceleration, or the Newton's second law in translational form. So I'm going to say that g sine theta mg sine theta minus force of friction is equal to ma, right? Because they are asking us to start with Newton's second law, and Newton's second law says that sum of all the forces is equal to mass times acceleration. We are supposed to find the net force. Okay, so the net force is actually indeed equal to this thing, right? This is the net force after all. Do we know the friction already? Do we know the coefficient of friction? No, we don't know. So we need to find the friction force, and I think we already have the friction force, right? The friction force from here is just from here in terms of, I'm sorry, friction force is just FF. So I can just say that mg sine theta minus FF is the required net force acting on the disk, and this will be F net. So I think that's our answer, right? I'm going to just say that sum of all the forces is going to be mg sine theta, and FF is also given to us, so I'll just box this in. All right. Try an expression for the linear acceleration of the center of mass of the disk. Express your answer in terms of this. Da, da, da. Okay, now I can say that sum of all the forces is mass times acceleration. But remember that the friction force should not be a part of our answer. All right, that's fine. MA is equal to mg sine theta minus FF. That's what we have over here. And if we, since we are trying to eliminate this FF over here, we're going to go back and borrow this equation. So from here, if we decorate this a little bit, 2 times FF multiplying MR both the sides, it will be alpha times M times R. So FF will be equal to alpha capital M R over 2. You might be thinking that you're eliminating FF, but you're introducing another variable alpha, which is also not allowed. That's absolutely fine. That's absolutely right. And we will eliminate alpha just in a minute. So I'm going to replace this. I'm going to replace this FF, which is alpha mr over 2, alpha mr over 2. M and M is gone. And we have now a relationship that alpha is nothing but A over R. That is a relationship between alpha and R. So all we are supposed to do now is just replace this alpha with A over R. So this equation is going to look like A will be equal to G sine theta minus alpha is A over R. So A over R times R over 2. That's what we have. Because alpha is replaced with A over R and R over 2 just remains as it is. So R and R is gone. We are left with A is equal to G sine theta minus A over 2. Adding A over 2 both the sides, I will get 3 over 2A is equal to G sine theta. So the acceleration will be 2/3 of G sine theta. 2/3 of G sine theta. And that is indeed our final answer for this part. Finally, over here, the last question. they have another experiment in which a block of ice rests on this inclined plane, and this is frictionless now, and it is also released. If the disk initially was taking T disk to come down, and if this is taking T block to come down, T is the time. So we need to compare these. So I think that would be pretty easy now because we already got this acceleration, right? The linear acceleration is 2/3 of g sine theta. And we very well know that this acceleration will just be g sine theta because there is no other friction force or anything involved over here. So if we use the equations of motion, we know that this has to be L and L for both the cases because this is identical. So if we use the second equation of motion, that L is equal to the second equation of motion is change of x is equal to v initial times t plus half at square, correct? Initially it is released, so that's 0, half a t square. Multiplying 2 both the sides, 2 delta x is at square, dividing by a both the sides, so 2 delta x over a is t square. In other words, t is the square root of 2 delta x over a. Now delta x in our case is just L, so it's clear that if the acceleration is less, time taken will be more, correct? So since this is accelerating with a lesser magnitude, because this is 2/3 of g sine theta and this is g sine theta, so time taken by the disk has to be more than the time taken by the block. That should be our final answer. Right. In this question, we are given that there's a block of mass and that is attached to an ideal spring whose other end is fixed to a wall. The block is displaced to a distance of x naught to the left of the spring's equilibrium position as shown over here. So this is the equilibrium is displaced to the left by a distance of x naught and is then released from rest and oscillates with negligible friction around the horizontal surface. When the block is oscillating, it has a maximum speed of V max over here, right? The energy bar charts in figure 2, there you go, we have figure 2, represents the spring potential energy US of the block spring system, and the kinetic energy of the block as the block passes through the positions negative x naught, 0, and positive x naught while the block oscillates. Now the bar chart at x equal to minus x naught, the bar chart at x equal to minus x naught is complete. Okay, this is complete for us, this one. Draw a shaded rectangles to complete the energy bar charts in figure 2 for the position these two. Positive energy values are denoted above the 0 line and negative are below. Shaded region should start at the dashed line representing the 0 energy, represent any energy that is equal to 0 with a distinct line on the 0 line, and relative height, relative height as well. So I think this should be okay for us because we know that since there is no loss of energy, and when it comes to the equilibrium, the spring is going to come at its natural length, and at the natural length, the spring won't really have any potential energy, right? So for us, this portion will just become 0 as soon as x is 0. So this is just a 0 over here, and the entire energy is going to convert into the kinetic energy of the block. So we're just going to draw a rectangle that is at the same height as the potential energy, that is at x equal to minus x naught. So this should be our answer. And when it is at x equal to plus x naught, then eventually exact same thing is going to happen. It won't really go negative because this potential energy's formula is k over 2 x naught square. So even if x naught is negative, it doesn't really make any difference because that's a square. So once again, kinetic is going to become 0 and the entire energy will be converted into a potential, spring potential over here. So that's what we have with the same height. All right, excellent. What is the next question for us? Let me just clear this up. All right, looks a little more decent. Um, Figure 3 shows the position. Let me zoom in. Figure 3 shows the position of the blocks. Uh, where's figure 3, by the way? Here. So it shows the position of the block as a function of time. And figure 4 shows the force exerted by the spring as a function of time. All right, cool. What is the question, by the way? All right, there you go. Using figures 3 and 4, determine an expression for the spring constant of the spring. What other information do I have? I see, I have Vmax, and you know what, I'm going to borrow this figure from here so that I don't have to go here and there. All right, let's keep it here. And let's try to use this information now. All right, I know that whenever the force is maximum at x equal to 0, don't you think this force is definitely the maximum one, right? And we know that at this point, so isn't that just the maximum force that is acting over here? We know that F max is equal to K times X max. And F max is just F max, and X max is X naught, right? It's given right here, X naught. So the value of K will be F max over X naught. That is K. All right. Now, starting with an equation for the period of the mass of a spring, derive an expression for the mass of the block, IC. Express your answer in terms of these things. Begin your derivation by writing a fundamental physics principle or an equation for the reference book. So I know that the time period for a spring mass system is given by 2 pi square root m over k. I need to find the mass in terms of all this. So I'm going to square both the sides because I need to get this away from the radical. Or maybe I can divide by 2 pi both the sides first. So that looks like this. Then I can square both the sides. So t square over 2 pi square is 4 pi square, and square of m over k root is just m over k because radical will disappear. I'm going to multiply k both the sides, so it will be t square k over 4 pi square is equal to m. However, in our answer, they do not need capital T and they don't need K as well. So that's fine. We can eliminate because from this curve, don't you think I have the value of the time period? It is 2T naught because that is eventually the time taken for one cycle, right? So I'm going to replace this capital T with 2T naught and 4 pi square as it is, and this is also square, and k we already found. It is f max over x naught. That is the value of small m. So small m comes out as 2t naught square is 4t naught square, 4 pi square, f naught over x naught. These two are gone. So finally the answer is f naught t square over x naught pi square, which is absolutely only in terms of um, these attributes that they mentioned over here. That should be our answer. In this question, in part C, they are asking us to graph the velocity time curve over here. All right. The period is not going to change. The period is still 2t naught, what was here, what we saw earlier, right? Okay, so it starts at x equal to 0. This is the point when x is 0. So this should again be the point. Sorry, it started at x equal to minus x naught. Sorry. So this should again be the point where it is at minus x naught. This should again be the point when it is at minus x naught. So don't you think it makes sense over here? This is 0 and this is x naught. So after half time period, it should come here because after another half, it will again come back. So half time period is over here. So at this point, it should be at x naught. X naught. So this should again be at x naught. So in between this, it should pass the equilibrium point because equilibrium point is the point where the velocity is maximum. So it will hit the maxima over here. Why is it positive? Because initially it is going to the right and right is positive. And then it will be going to the left in the second half, which will be negative. So it should look like this. It should go up, then it should come down, then it should come down, then it should come up. Okay, so this is the first cycle, and likewise you have to just repeat this one. So it will again go up, come down, keep moving down, and then eventually come up. So this is how, and this value will be negative V max over here. So that's how the situation should look like. It's basically a sine curve. It has to be a sine curve. All right, I think we do have one more part. A student sketches the free body diagram in figure 6 and makes the following claim. The free body diagram shows the force exerted on the block at t equal to 1.5. And they are asking that justify why this is not consistent with the graph of velocity as a function of time. Because the velocity as a function of time at 1.5 is giving me minus fx naught, minus v max, right? And as I can see that the slope of the velocity time curve gives the acceleration. And if I draw a tangent, slope of the tangent, I mean, gives the acceleration. And if I will draw a tangent at 1.5 t naught, which is right here, the slope is 0, which means that the acceleration is 0, which means that the F net towards the horizontal side should also be 0. But that's not what the student has shown. He has shown a net force towards the horizontal. So that is not consistent with the curve of velocity time that we drew earlier because of this reason. Okay, all right. Here's a question. This question is based on fluid mechanics. Let's see what it has to tell us. There's a container over here, and that container has a liquid in it. Let's read this out. A group of students are given a cylindrical container half filled with a liquid of unknown density rho. The students have access to an additional container with more of the same liquid, meter sticks, and a pressure sensor. Do not have access to a scale. Okay. So what this means for us is no scale means no bathroom scale. No bathroom scale means I cannot measure weight, but I can measure the length, of course. I have a meter stick. All right. Now the students are asked. Okay, the students are asked to take measurements to create a graph that could be used to determine the density of the liquid. Describe an experimental procedure that the students could use to collect the data needed to determine the density of the liquid. Include any steps necessary to reduce experimental uncertainty. If needed, you may include a simple diagram of the setup with your procedure. All right, so how do you think we can do this? It is half filled, by the way, and there is an unknown density. We have more liquid, meter stick, and a pressure sensor. So I think I'm going to use the equation of the absolute pressure because we can measure pressure, right? And absolute pressure is the atmospheric pressure plus the gauge pressure, PG. Atmospheric pressure is a constant value, 10 raised to 5 pascals. Uh, PG is given by rho GH, right? Now, this is what I need to find. Let me write a rho first. That is the unknown. G is a constant and H can be measured. So this is the equation that I'm going to use. And what I'm going to do is I'm going to fill this liquid. Initially, see, I have the meter stick, right? So I'm going to measure this length. So I'm going to describe how the data collected. So I think we can answer part A and B together because they're asking how the data collected could be plotted to have a linear curve. So what I'm going to do is in my experiment, I'm going to measure the pressure at the bottom. So right now I'm answering part A where how can I experiment this? I'm going to measure, first I'm going to measure the height of the liquid, which is half filled right now using a meter stick. And I'm going to measure the pressure at the bottom because of the pressure sensor. And I'm going to note down in this table. And this table, I have the P absolute, which is what I'm going to measure. And I'm going to measure the height as well. All right. So P absolute and height comes in this table, P absolute and height. Then I'm going to, so at the same instant, since we have to reduce the uncertainty as well. So after saying that, I'm going to measure height and pressure at the bottom. I'm going to repeat this procedure 4 times. Repeat 4 times so that the uncertainty is reduced. and take the average of those values. Take the average of those values. Then in the next step, I'm going to repeat, rather I will just put the Roman numbers here so that it's not confusing. Then I'm going to pour some more liquid to another height and do the same procedure. So next step is pour more liquid. Once again, measure height and absolute pressure at the bottom and repeat 4 times and take average. And repeat this for at least 5 readings, so 5 different heights. So we will have absolute pressure, height, reading 1, reading 2, reading 3, reading 4, and reading 5. And then and as we can see that and describe how the data collected. So what I'm going to do is I'm going to plot this on the y-axis. As we can clearly see, this is already a y-axis, and the h will be on the x-axis, which is over here. So this will look like y equal to mx plus b, where the value of m gives me the value of rho times g, and b is just the atmospheric pressure, which has a value of 10 raised to 5 pascals. So this is how we can make a linear graph between y and x, where x is the height and the slope can give me rho g. And this slope I'm going to divide by the acceleration due to gravity and find the unknown density over here. So that should be our answer. Okay, now they are performing another experiment with another cylinder which is filled with water as shown over here. The students make a small hole at the side of the cylinder and measure the speed v at which the water exits the hole. The students plug the first hole and make another one at different height and repeat this procedure. The following table shows the height of each hole related to the top of the water, and the students make the corresponding water speed. So they now have a relationship based on various heights and the speed of the water. The students correctly determined that the relationship between h and v is given by this. Now the students create a graph of v square on the y-axis. Indicate which measured or calculated could be quantity could be plotted on the horizontal axis to yield a linear graph whose slope can be used to calculate an experimental value for the acceleration due to gravity. Obviously this one is easy, it's just a lot of reading, because the moment you will square it, you will get v square is equal to 2gh. So it makes sense that if this is y, this has to be the slope and this has to be the x value. So this will become y equal to mx, where the slope can be used to find the acceleration due to gravity by just dividing by 2. So vertical horizontal axis should definitely be the height h over here. Now on the grid, plot the appropriate quantities to determine the acceleration due to gravity. Clearly scale and label all axes. Right, so this is our grid. First, we need to find the value of v square over here. So I'm gonna do that over here real quick. Please bear with me for a couple of minutes. 4.84, 2 square is 4. 1.8 square is 3.24. 1.4 square is 1.96. And 1.1 square is 1.21. Now I'm gonna plot this. So first I need to determine the axis over here. So I think it is going from 0.05. That's pretty straightforward, right? Like 0.05, 0.1, 0.15, 0.2, 0.25. Do I have the 5 markings here? I think so. This is 0.05, this is 0.1, this is 0.05, this is 0.1, this is 0.15, this is 0.20, and this is 0.25 over here. 1, 2, 3, 4, 5. We have 5 readings. 5 markings over here, and this is 0.3. Now the first point is 0.25 and then 4.84. So 0.25 is on this axis and 4.84. I know that this is 4.2, 4.4, 4.6, 4.8. So 4.84 is probably somewhere over here. Right, I hope you're able to see that. Let me use a blue color rather. Okay. Then I have a 4. Well, 4 is easy. 4 is over here in the y coordinate, and 0.2. 0.2 is over here. So that should be the point, right? This should be the point. Then I have 3.24 on the y and 0.15. So 0.15 is easy. That's somewhere over here. And 3.24 is 3.2 is somewhere over here. So it's around this point. So it should be somewhere over here. Right, the next point is 0.1 and 1.96. 1.96 is around 2, right? 1.96 is around 2. 2 is over here and 0.1 is over here. So that's somewhere over here. And this is 1.2 and 0.05. 1.2 is this and 0.05 is here. So this is how it looks like. We have to draw a line of best fit as well. So let me try to draw as accurate as possible. So probably this is going to look something like this, and not bad, not bad at all. Right. And after the line of best fit, we need to find the experimental value for acceleration. So for that, we need to find slope. For that, we need to find two nice and easy points over here that are passing through the grid. Uh, I would take probably one point as this one. This point is 0.1 comma, so this point, let's call it A, is 0.1 comma 2.2, and let's find another point B. B is somewhere over here, which is 0.21, of course, and the Y value is 4.2. What is the slope? Slope is y2 minus y1 over x2 minus x1. Okay, let me quickly do this. It's 2 over 0.11. That's coming as 18.18. 18.18 over here. And then we are going to divide. And that's pretty much it, because I just need to, like I said, slope is twice of g. So the g is going to be uh, slope divided by 2. So that's 2 times 9 is 18, 9.09 meter per second square, which is a pretty decent value. It's around 9.8 is the actual 9.81. That's what we take. But yeah, this is a pretty decent value. So we're going to take that, and this is actually pretty much our answer. Right, this type of FRQ is qualitative or quantitative translation. There's a block 1 of mass m1 that slides to the right along a horizontal surface with a speed v0 towards block 2 of mass m2, which is initially at rest. When block 1 collides with block 2, they stick together, and the friction between the blocks and the surface is negligible. That's great. If block 2 is much less massive than block 1, estimate the approximate speed of the two block system after the collision in terms of V0. Justify your estimate using qualitative reasoning beyond referencing equations. I think it makes sense that if block 2 is much less massive than block 1, so okay, the equation says that momentum is conserved, right? So if the momentum is conserved, the initial momentum m1 V0 of block 1 plus momentum of block 2, which is 0, will be equal to m1 plus m2 times the new velocity v. So dividing both sides with m1 plus m2, the velocity is just v. Now it makes sense that if m1, m2 is much less than m1, there will not be any effect of the collision, right? It's like a very big block collides with a small block. I mean, what can the small block do for the velocity? Nothing. The velocity is going to almost remain same, which which makes sense qualitatively, and quantitatively, of course, m2 is less than m1, which means that this m2 can just be ignored, because m2 plus m1 will be almost m1. I mean, if you do 1 kilogram with 10 grams, that's just about 1 kilogram only, right? 10 grams is not going to make a huge difference. So this will become approximately mv0 over m1. These two are cancelled, and v will be about v0 only. There will not be any huge change. There is not any substantial change. You can also support your statement by saying that the momentum, since this velocity is, sorry, since this mass is very less, right? So eventually this momentum will also be very less. And after all, we are conserving the momentum, right? So initial momentum is only of block 1. The final momentum is of block 1 and block 2. And since the block two's momentum is very, very less, this can be ignored, which means that the initial momentum and final momentum are same. So initial velocity and final velocity will also be same. That's all. Uh, that's also something that you can use by referencing momentum. Okay, B says that starting with conservation of momentum, derive an equation for V final, the speed of the two block system after the collision. Begin. Okay, so that's something that we have already that we already did last time. We already have our equation, right? So I can just copy and paste this over there, because that's why the only difference is we will not be doing any approximation this time of the mass. So this will be the V final over here. And we have started with the conservation of momentum, of course. So after conserving the momentum, that's how the situation looks like. Finally, if block 2 is much less massive than block 1, does the equation you derived in part B agree with the qualitative reasoning? Yes, definitely it agrees, because if M2 is very, very less, then this can be ignored and M1 is cancelled, and then of course the final velocity is just same as the initial velocity. So M1 V naught over M1, which is just V naught, so V final is about same as V naught. So I think in this question, we can just ignore writing the equations part, because it's not like they are going to deduct marks, but that's not something that they want us to show, because they want us to explain it beyond the equation. So you can just say that the momentum is conserved. Momentum is conserved. Momentum is conserved. That's the first thing. The final momentum of block 2 can be ignored because the velocity is very less. This means that the initial momentum of block, that it means that the final momentum is only of block 1, and that is also same as the initial momentum because it is also of block 1, which means that the final velocity is about same as the initial velocity. And that's how you can conclude question 1 without referencing equations, because they are anyway making us use these equations in the coming parts. So that's how we can solve this question.